Thanks. Um, um, First of all, my talk will not be about physics and will not be about combinatorics either. But still, I hope it can somehow be relevant and it can be inspiring. I want to demonstrate three very basic ideas in mathematics with my talk. The first idea is if you want to calculate critical points, what you are really doing is you are doing some intersection theory or doing some intersections in the cotangent bundle. And second idea is, in some cases, you can translate, or using this index theorem, you can translate intersection numbers in cotangent bundle into Euler characteristics. And the last idea is, well, if somehow Euler characteristics are not enough, the generalization are Chern classes. So the top Chern class is the top Chern class of the tangent bundle is Euler characteristic. And if you see the other Chern classes, you get more information. Now, I start with the objects that will be we'll discuss through the talk. The motivation comes from applied math, from optimization problems. So in optimization problems, the goal is to find the maximum or minimum value of a function on a space. Okay? And for us to apply our machinery, we will restrict ourselves to the scenario when the space and the function are both algebraic. So now we are thinking about like a real algebraic variety or semi-algebraic variety and maybe a polynomial function on the variety. The question is to find the maximum and minimum value of the function. And then this leads to the following complex problem. So the idea is, well, solving things over the real can be tricky. So what you do is you try to solve the problem over complex numbers. For complex numbers, there is not a maximum or minimum value. So what you do is you find all critical values or critical points, and then you check which are real, and maybe among the real ones, maybe you can find your maximum or minimum value. Okay, so and this actually happened. So this particular problem actually happened or occurred in some of the previous talks, where the case is specialized on hyperplane arrangement complement. And now we are thinking about a general variety in the affine torus. And we look for the critical points of this power function. And this was also called the master function, or maybe also a Marchenko function. Or I mean, there were questions about how many critical points does a general function xi to the ui power have. Okay. And I allow x to be singular. So when I talk about critical points, I only consider critical points on the smooth locus. But in general, x can be singular. So before, when x is hyperplane, arrangement complement is always smooth. And one remark is if ui are general, it turns out that it does not depend on the exact choice of ui. As long as they are general, the number of critical points will be the same. And the number of critical points in this question are called maximum likelihood degree. Outside Zariski, okay, on a Zariski open set. On a Zariski open set. Yes, it's Zariski. And in fact, if you think about this more carefully, I can allow ui to be complex numbers. So then the function will be multi-valued, but critical points still make sense. So if one branch you have a critical point here, every branch will have a critical point there because different branches differ by a scalar. So I can really, if you want, make ui to be complex numbers. And then you can say on the space of all the ui, there will be a Zariski open set where I mean, we'll see this. You'll see this more clearly later. Okay, so why people are interested in this question? So this number somehow characterizes the complexity of this optimization problem. If you know you have 1,000 critical points, you know the problem will be complicated if you want to like numerically calculate. If you know there are only 3 critical points, then there is a good chance your computer can solve the problem. And also, if you know the number of critical points, there are algorithms that can compute the critical points one by one. If you know there are 3 critical points and you hit the 3rd critical points, you can stop. It gives you a stop criteria. Okay. Then there is a similar problem where my variety lives in the affine space, and I consider linear functions. And for general linear functions, again, the number of critical points will be independent of the particular choice of CIs. And this is called the linear optimization degree. I know this linear optimization, usually I know maybe you have a different meaning, but we couldn't come up with a better name. So let's just call this LO degrees. Linear optimization on algebraic varieties. Any question? Okay. Yeah, feel free to ask questions. I don't have much material, and also I try to want to make stay on the like basics, and if you have any questions, feel free to ask. Yes. So later I will draw a picture. Maybe hopefully the picture will convince you. Yeah, actually, every talk so far had different pictures. My talk didn't have a picture, so last night I decided to add a picture. So there will be one picture. I hope it will be useful. And I want to make one remark. So this particular problem, we were led to consider this particular problem because of a different problem, which was the closest point problem. The closest point problem asks to minimize this function for general value of Ci. And then if you think about it, if you introduce a new variable, so you embed your affine, so you have a variety x in Cn. If you use one more variable and embed your x to Cn plus 1, so a bigger dimensional space, maximizing this function or minimizing this function is same as on the bigger space kind of minimizing or maximizing a linear function. Now I want to explain how I think of this critical points as some intersection in cotangent space. So a critical point, if you think, okay, so before everything, a critical point by definition is f has a critical point means partial f, partial xi are all 0. And if you have a function f, let's say a holomorphic function, there is also something called a df, which is a holomorphic one form. df look like this, sum of partial f, partial xi, dxi. Let's say xi are the local coordinates of the manifold or the variety. Then you see, being a critical point is same as this one form vanish. Okay. And now I want to, so this kind of led to say the critical points are basically, to find critical points are basically to find where the one form vanishes. Okay. And on the ambient space, I have this cotangent bundle, which are the space of points, and at every point I consider the one form. Like at every point I have a point and together all the possible one forms. And I put them together, this is the cotangent space. And okay, right, so the cotangent space of C star to N has a natural trivialization. So I can kind of naturally write it as a product. Because C star N has a group structure. I mean, that's a precise way to say it is. And I can explicitly write down this coordinate Cn, the other factor, which are just one forms, like global one form like this. So a point in the cotangent space, I can think of it as a point in the torus together with a one form like this. And within this cotangent space, if I have a sub-variety X, I have something called conormal variety or conormal bundle, which is the space, which is the sub. I mean, so first of all, on the X coordinate, I need your point to lie on X. Now X is in C star to the n. And on the second factor, I consider all the one forms whose restriction to X vanishes. So okay, my notation here may be a little misleading. Let me change my coordinate to be Z, because X and C star to the n may have different coordinates. Okay, so X is a subspace. And kind of the same reason here, the one form vanishes is same as this function has a critical point at X. So here, the point is I have to take the function, this power function, on C star to the n, the function has no critical point. But once you restrict to X, there will be interesting critical points show up. And so in the language of one forms, I consider all the X and all the U such that the restriction as one form vanishes at the point X. Or I can think of reformulate in terms of functions, then these are the things that have a critical point. So in other words, the Conormal variety in the second formulation, you can think of it as the total space of critical points. So instead of I just take one function, I look at the critical points, I look at all functions and all the critical points together. And now I'm really allowing UI to be a complex number instead of an integer. As I've just said, if I have a complex number as power, I have a multi-valued function, but different branches differ by a constant. So the critical points are still well defined. Any questions? No? So the definition of ML degree is the number of critical points. And if you think about it, now I want you to look at this picture. So the red is the universal family of critical points. And what I'm doing, or the universal family of critical locus of one forms. And what I'm doing here is, okay, yeah, again, because I have to oversimplify the picture otherwise. I mean, I'm talking about Cn cross C star to the n. And over a complex number, when I draw it, I oversimplify the picture. And the blue line is I fix some general UI. That corresponds to choose a point in this vertical coordinates. Once I choose a specific UI, that gives me a horizontal line. And then I look at the critical points, those will be the blue points, the green points, sorry, the green points. And I could move this blue line up and down. You see, as long as I don't hit this kind of strange place where I have a more like a multiple intersection, I mean higher multiplicity intersections, the number of critical points will stay the same. Maybe this is related to some of the earlier questions. And now there is another way to think about the intersection of the three green points. The other interpretation is I do a projection from this blue, the red curve, which is the conormal, I project to the vertical factor of the UI coordinates. And I ask, what is the degree of this map? The definition of degree of a map is basically I choose a general point in the target, and I look at how many points are in the how many points in the pre-image. And that's exactly like you are drawing a line here and see how many intersections you have. And you can see there will be some branching locus, and also the red curve will not be really like, so this map projection may not be proper because C star to N is not compact. So there will be some strange behaviors, but the strange behavior will only live on a Zariski closed subset. So generically, you have a covering phenomenon, and the covering degree is the degree. Is the degree of this map, which is the ML degree. So I mean, maybe the one reason it's called ML degree is because you can literally interpret it as a degree of a map of algebraic varieties. Any questions? Yes. No, X is a subvariety of C star to D.
Yeah, but in this particular case.
Yeah. Well, if X is C star to the N is more or less trivial because all functions, all this kind of power functions will not have critical points. So if X is the whole C star to the N, the conormal will be the zero section of the product. So in this product, it will be C star to the N cross 0. So if I take so the red curve will be a horizontal line, which will be not so interesting. So you only see this kind of curly picture. I mean, because I don't have too many dimensions, right? So it looks like it dominates the C star to the N. No, it doesn't dominate. Because yeah. So yeah, the projection of the red to this horizontal direction is X. But because I just don't have enough dimension to demonstrate that. Okay, very good. Any other question? Okay. So ML degree can be considered degree of a map. Now I want to say the same thing. I mean, you can draw the same picture for linear LO degrees, and it's essentially the same. Again, I'm secretly using the fact that the affine space also has a group structure, and I have this notion of parallel or invariant one forms. Now, oh yes.
So if you imagine the monomial that you have, so x raised to the u, you take the log of this monomial, the u is the coefficients, and it's the sum. Is there anything you can do to a variety if you're looking at now with some transformation of that variety to get a variety that then gives you that?
Oh.
Are these related?
That's a good question. The answer is no. I mean, you could, but I don't think it will work. The reason is because for us, the variety has to be algebraic. If you replace X by a non-algebraic thing, everything will break. So your transformation will involve some log function, probably. And that will break the whole picture. Yes. So it's very important. You can say, what if I have a submanifold, complex submanifold of affine space or affine torus? None of this will work. So there will be like this kind of essential what's called in complex analysis, essential singularities at infinity. So those things will just break all the theory we use. Okay, now if X is singular, there is also a conormal variety. So when X is smooth, this conormal variety is actually a conormal bundle over X. But if X is singular, what do I do is I can still define the same thing, but now over the smooth locus, I define it to be the bundle, and then I take closure in the cotangent. So these are called conic Lagrangian cycles in the cotangent space, and they play an important role in the, for example, in this microlocal analysis. Okay. Now, I want to kind of demonstrate my next point is the ML degree and L degrees have topological meanings. So they are actually up to a sign, they are all recursive of X. So on the affine torus, they are up to a sign all recursive of X. And for the linear optimization, for the linear functions, the number of critical points will not be the all recursive of X, anymore. But now you have to remove a general affine hyperplane and compute the remaining part, the Euler curves. Okay, from a more theoretic point of view, what you do is you need, like, if x is in C star to the n, this power function will map x to C star. So you kind of want to map to C star because C star has no Euler characteristic. So the Euler characteristic of x are captured by the critical points. If you do a linear function from x to C, okay, now x is in Cn. From x to C, because C has Euler characteristic 1, that's not good. So what you do is you remove H. I don't know if you can still read, and you map to C star. Then you can explore the nice property that C star has Euler characteristic 0. So all the kind of Euler characteristic here come from critical points. That's the reason you remove a hyperplane. Any question? And the theorem all look the same, but somehow the proof all involve some non-trivial, like math or theory. So the Wernicke-Kaplanov, they use D-module theory. Jun has a proof of this case, which use Chern-Mather class. And then the Siade, Tibar, Wowiowski, in the linear case, they use stratified Morse theory of Gorski-McPherson. And then with collaborators, I came up with 2 more elementary proofs that use non-proper Morse theory. So the main problem is the X is not compact. If you use most kind of index theory or global theory, it requires compactness. So you have to kind of deal with this non-compactness, and that's where the most of the difficulty comes in. Any questions? Let me give you a 2-sentence proof, 2 or 3-sentence proof of the Wernicke-Kapranov's proof. So they proved for a smooth subvariety of Ivan torus, the ML degree equals up to a sign Euler curve. Okay, let's prove this. There is this global index theorem, which says the Euler characteristic of a D module can be computed by intersection numbers of some cycles in cotangent bundle. The theorem originally, due to Dobson and Kashiwara, are for compact varieties, and Ginsburg could extend this to non-compact. So we just apply. Okay, I'm not gonna write down the formula. I just kind of give you a flavor of what's happening. So you can apply this formula to the D module. So X is a subvariety of C star to N. You have a constant D module on X. X is smooth, so there is a nice constant D module on X. Push it forward, and then you have a D module on C star to the N. Apply the index formula. And then so the index formula says the Euler characteristic of this D module is some intersection of something. These are essentially what I draw earlier, the red and the blue. And then they give you the ML degree. ML degree is again, we have demonstrated, it can also be interpreted by intersection. And that's the proof. And here, because for this D modules, when you put forward, you kind of shifted it, and then it lives on a different degree. So the sign kind of being absorbed here. So this is up to a sign equals to Euler characteristic of X, and that's ML degree of X. Yes.
So this theorem applies to Marchenko's conjecture.
This proves Marchenko's conjecture. Yeah, in full generality. Even in full generality. So this proof generalized to X singular. So most of the other proof doesn't. This even works for X singular. Any other question? So we use the, and there is also a similar, I mean, okay, there is also the other formula for L degrees. We use this 2 formulas to prove some conjectures of, okay. of, let me just say, Bern and some of his collaborators had different conjectures, and we could use the topological formula. So they conjecture ML degree or this ED, this minimum or closest point degree is certain number, and we can use the topological formula to confirm their conjectures. So that's kind of how I first got involved in this problem. And now I want to extend the theory to singular varieties. Singular varieties may be kind of difficult using the classical method, but with this D modules and with this kind of macro-local analysis, they are kind of as nice as smooth ones in some sense. So they don't have really additional difficulty as long as you accept some kind of topological invariant. Okay. So if your variety is singular, the formulas will fail for sure. If you just compute all accuracy, the formula will not work. But you can fix it by doing a weighted all accuracy. So the all accuracy will not really capture the ML degree. So you have to do a weighted all accuracy in the sense that you on the singular locus, you do some weight. Again, the singular locus can be less singular locus, more singular locus. The singular locus can have a stratification. And you have to put right weight on each strata, and then you do a weighted all accuracy. And this in singularity theory, this is called local Euler obstruction function. So local Euler obstruction function give you a number, an integer, on every stratification of the singular locus. So with a singular variety, there is some kind of Wien stratification, stratify the space, and you put a number, or this local Euler obstruction function, put a number on every strata. And then, so you take this weighted Euler accuracy. So let's do an example. Oh, sorry, the example is the next page. So, okay, I want to say the Euler obstruction function is 1 on the smooth point. So if your variety is smooth, you are just weighted by 1, nothing happens. But on the singular locus, it can have different values. Let's do, okay. Before doing example, let me tell you what the Euler obstruction function is for a curve. I don't know what's the number of this multiplicity, or if it has a number in algebra. If you have a plane curve, suppose you have singular point P, then you look for the largest K such that F is MP to the K. And then this K is the Euler obstruction function at that point. Now we can do an example. Let's look at this plane curve in C star square. So this is a cuspidal curve. So I move the cuspidal singularity to 1, 1 because I'm gonna remove all the coordinates. So if the singularity lie on the coordinates, it would not show up. Okay. And this curve I want to compute, first I want to compute the Euler accuracy of this curve. So the curve in C star is a cuspidal curve in C2 with 5 points removed. I just count how many points does this curve intersect with the coordinate planes. And you can just easily see 3 here, probably 3 here, 2 here, so you remove 5 points. So the Euler accuracy of the curve in the C star square will be 1 minus 5 because the Euler accuracy is additive on algebraic varieties, which is minus 4. But if you put minus 4 in the formula, it will not give you the correct answer because you have to take into account the singularity of the cusp point. With the above formula, you can check the K is 2 here. This function, it lies in M squared, but not in M cubed. So the Euler obstruction is 2. So that means you have to weight the singular point with multiplicity 2. And everything else is 1, so just like before. So now when you compute Euler accuracy, you just compute the original Euler accuracy and plus 1, because you have an additional weight of the singular point. So the Euler accuracy of the Euler obstruction function is minus 3. And then you plug in the formula, you know ML degree is 3. In this case, actually, you can easily verify this. You can parameterize the curve by t and just compute how many correct points, write down the function. You can verify it is 3. And if your variety has larger dimensional, the singularity gets more complicated. This Euler obstruction function in general can be hard to compute. But if it's usually isolated singularity, it will not be so hard to compute. And if somehow your variety, for example, has a group action and there is some natural stratification, usually in some good cases, you can compute this Euler. But once you accept this Euler obstruction function, the formula is just like before. Not necessarily. Not necessarily. I think the like more singular the curve is, actually sometimes the simpler the curve is, right? Like you have a nodal P1 is something like a curve. So sometimes the number of correct points can decrease. Is that your question?
Yeah, I'm just looking at your definition, and it seems like you always add.
Yes. Okay. So if that's your question, so the answer is you in general no, because the Euler obstruction function can have negative value. Well, for even for isolated point, if the dimension is higher, you could still have a negative value. So it's the Euler obstruction the usual Euler accuracy will not give you a lower upper bound in general. Any other question? Okay. Now I'm coming to kind of the last part of the talk. So now I want to generalize the ML degree and L degrees. And one way to generalize it, if I start with this variety in affine torus, what I can do is I can take general hyperplane cuts I times. And then I get a new variety, and I compute its ML degree. I can let this I vary from 0 to the dimension of x. So the last, if I equals dimension of x, you can see you get a bunch of points, and the number of points is exactly the degree of x. So it's kind of it's something kind of connect both the usual notion of degree and the ML degree. Like the zeros, the zeros SI is ML degree, and the top SI is the usual degree. And there is also a notion called ML bidegree. So basically, start with the variety, you get two sequential numbers. ML bidegree is you take this conormal variety in C star to the n cross Cn. Okay, so this is one way to define the bidegree using homology groups. Okay, you can rewrite so it represents the homology class in a space which is poured out 2 Pn. You take closure in Pn cross Pn, and then you can now by Kuhn's formula you can write the class in this kind of sum in a unique way, where I'm thinking Pk is a linear subspace of Pn and Pn minus k is a subspace of Pn, and this is how you write bidegree. And another way, maybe slightly more intuitive way to think of bidegree is you start with this conormal variety. It sits in C star to the n cross Cn. But then what you do is you take so you kind of complete this to Cn cross Cn, and then you take a general projection to C, maybe minus k cross Ck, where this Cn minus k is a general subspace of Cn, and this is a general subspace of this Cn. And then you do the same degree. So then you have something here, you map in here and map down. They have the same dimension. So if you consider this map, the degree of this map will be bk. So this is like the the degree just like the ML degree with the definition I had in the picture earlier. And if you like, there's a different topological definition using homology group. So they are more refined invariants, kind of measure the complexity of the maximum likelihood to compute the critical points, because it's a refined, right? Because compute ML or the critical points are kind of doing some intersection theory with this variety, the Conormal variety. And this degrees, especially the ML bidegrees, measures the complexity of this Conormal variety. Oh, sorry, where is this? This Conormal variety in a more refined way. Okay. And if k equals 0 or I equals 0, they both give back to the ML degree just by definition, or almost. And this one, if you see, okay, if k equals 0. Okay, maybe I put the k in the different, maybe it should be like k here and minus k here. You should get the ML degree. And then this was again a theorem and also a conjecture that motivated some of the research here. Is so there's two sequential numbers. If you think of the formula looks complicated, but the idea is very easy. So you have two sequential numbers out of x, which is the sectional degrees and bidegrees. And these two sequential numbers are related by like a linear transformation. But there is the only way to express this linear transformation is through this seemingly complicated formula, but it's actually not so bad because it's indeed a linear transformation. So you see, so here u and p are formal variables. This bold u and p are formal variables. And so what is Sx? It's just a polynomial in the formal variables, and the coefficients are the s. And you see, if I plug in p and u minus p to this formula, what do I get? I guess many monomial coefficients multiplied by Sn. So the coefficients are some linear combinations of the s, but with some additional monomial coefficient and some linear combination. And this will be an easier formulation. And also things will show up are some of the maybe S0 will show up, or okay, S0 will only show up here, and you do some difference. You do a division of the formal variable. So in the end, you get a new formula, a linear combination, basically, of the SIs appearing as the coefficient here. And you have a reverse or inverse formula that goes back. So basically, like if you compose each other, you get back to the identity. Okay, so anyway, there's some linear transformations that relate S and B. And this formula was proved first by Jun and Byrne for smooth X. Okay, so my remark is here. So it's proved by Jun and Byrne, assuming X is smooth and shown. Shown means the boundary behavior is nice. It's like normal crossing, or to some tori variety is normal crossing. And they conjecture this is true for arbitrary irreducible subvarieties. And the conjecture was proved in a joint work with Maxim Rodriguez, and they. So what is the idea of proving this? Or better question is, how do we understand the bidegrees and the sectional degrees? And the idea is use Chern classes. Okay, this is already in the work of Drew and Byrne is you. Okay, so now saying Chern class is a little bit tricky because X is not compact. But McPherson has this kind of Chern class. So McPherson has a theory to define Chern class for varieties that can be arbitrarily singular or non-compact. Okay, McPherson has a way to talk about Chern classes. Basically, we just use McPherson's language of this variety X. And now what I do is I actually think of X, because again, where the Chern class live is also a problem. You don't want to say the Chern class of X live in the homology group of X, because the homology group of X may not be so interesting because X is affine variety, for example, all the higher homology group vanish. So you actually want to think X lives in Pn. So when you talk about homology group, you want to say they live in the homology group of Pn. So basically, there is a notion of Chern class of X in terms of the cohomology group of Pn. So you think X is something living in Pn, and you can define this Chern class of something living in Pn in terms of cohomology group of Pn. That's the Chern class. So here we need to use Chern-Mather class. It's different from the usual CSM class, the Chern-Schwarz-McPherson class, in the sense that it's a weighted CSM class. The weight is exactly by the Euler obstruction function. Just like you don't want to take Euler characteristic, but you want to take a weighted Euler characteristic. So here you don't want to take the usual CSM class. You take a weighted CSM class. That will give you the correct answer. Okay. And then the BIs will be the ML bidegrees. Okay. So this is proved. Okay, maybe I should also put Jun and maybe Bernd's name here for if X is smooth and shown. And then we generalize that to arbitrary irreducible subvariety. Okay. And then once you can relate this bidegrees with Chern classes, then Luffy has a very nice formula which can kind of, once you know the Chern class of X, it tells you the Chern class of X with a general you can, so if you know the Chern class of X, you can take a general hyperplane cut of X. Luffy tell you if you know the Chern class of X, his formula tells you what's the Chern class of X intersect X, of X intersect H. Okay. And you can iterate the formula and then you get all this further intersections. So basically, once you know the Chern class of X, you know Chern class of all the sections. So that relate that kind of, once you know BI, you know the Chern class, then you know the Chern class of all the intersections, and then you reverse the formula, you get all the BI. That's kind of the idea. You can one sequence determine the other sequence. Any question? And similarly, you can do play the same game for this linear functions. Okay. We call this LO degree. So you can still define the same LO bidegrees. Again, the conormal variety now lives in Cn cross Cn, and you have a bidegree. And you also can start with the variety. You can take a hyperplane cast and then take LO degrees again. You have this SI. But now, if you want to ask what's the relation between SI, they are equal. Basically, because the whole variety, I mean, everything is defined using like linear sections, so linear casts, and it just turns out this is same. Okay, it's proved by again Bernd and his collaborators, and we have a different way to argue this more topologically of this. But then you can also ask, what is the relation between the bidegrees and the topology and the Chern classes? Well, the two bidegrees are same, or sectional degree and bidegree are same. So I can just take one of them to be, okay, I take the BI. And I can, again, talk about the Chern classes of X in Pn. So I can write in this kind of form. Then the relation between AI and BI is again through some linear transformation. And now it has a slightly simpler way to formulate. I mean, again, you can imagine, if you know AI, you expand this, you have some linear combination with some of terms as binomial coefficients, you get BI. And conversely, you can go back. Questions? Okay, no, I'm definitely going faster than I thought. So I have a few final remarks before I end. Let me see what do I want to say first. Okay, so C star to the n, in some sense, this problem of relating the Chern classes and bidegrees remember for C star to the n, we know the Chern classes and bidegrees are same. So what's the reason for that? This is because the logarithmic Cotangent bundle is trivial. And all these parallel sections, remember this UI, this product of, okay, let me see, maybe BI, eraser, okay, maybe I just write here. So remember we have product of xi to the ui, or these are the like parallel functions, and I can take the one forms. They look like sum of ui dxi over xi. They are like parallel one forms or translation invariant one forms. So this one forms exactly are the global sections of the logarithmic Cotangent bundle. So when you do intersections, you are really like doing some intersections on a trivial vector bundle. So which is good, which is the reason the formulas relating bidegrees and the Chern classes are just equality basically. But the formula becomes more complicated here for the linear optimization. The reason is now what you want to relate this kind of forms. Now the forms look like this: sum of ci dxi. They no longer have the poles anymore, and they will not be. I mean, at the infinity, they will have worse poles than the logarithmic poles. So then you have to twist the logarithmic Cotangent bundle one more time to exactly get those sections. And what you do, you untwist this. This is what happened, what the twisted did. That's why, yeah, the bidegrees and Chern classes are not the same. Questions? Two more remarks, then I'll be done. Okay, there is another paper I wrote with Jose Rodriguez where we can kind of reverse engineer, and we say, well, now suppose your motivation is different. Suppose you are a topologist and you want to, or in singularity theory, you want to understand what's the Euler obstruction function. You want to compute Euler obstruction function. So now what you do is you can actually compute a bunch of ML degrees. Well, ML degrees are just number of critical points on a certain space. Which you can do by solving polynomial equations. So now you just kind of, so we have an algorithm that if you give me a affine variety with a point, a very affine variety or a variety C star to the n and a point in x, I can kind of chop x in different ways, get a bunch of new like locally closed subvarieties of x, and compute the ML degrees of the subvarieties. And I do like an alternating sum of this ML degrees, and I can recover the Euler obstruction function at a point. So we can give actually a computer algorithm to compute Euler obstruction function, which is, and now Paulo Alufi just told me he had another formula to do this, but our work was like almost 10 years ago, and there were no like algorithm that can compute. Like the topological formula uses autoccuracy of some complex links. There is some analytic object that computers just are not, computers cannot compute. But with this kind of algorithm, we can compute Euler obstruction functions. Okay, the last remark is we also had some work understanding this kind of non-generic behavior. So throughout the talk, we assumed UI to be generic. So now what if X UI are not generic? So by not generic, I mean, for example, critical points can collide. There can be a higher multiplicity critical point. Or in the worst case, I can have a positive dimensional critical locus. Or maybe the critical point can be at infinity. I'm just not counting the right number. So what you do is you perturb the UI to generic, and then you move the UI from generic back to your special value. And then all the way, it will always be generic until the very last moment you hit this non-generic value. So basically, you have the correct number of critical points, and they move in your space, and they stop somewhere. Or maybe they escape to infinity, or they stop somewhere. we can understand this kind of limiting behavior pretty well as long as the critical point does not escape to infinity. We have very intrinsic topological formulas to tell you where the points go, and there will also be behaviors where several critical points will collide at some point. I can tell you where it collide and how many multiplicity it collide. But one thing I don't know is there could be points go to infinity, and in some examples there are points go to infinity, and I just don't know how to control them. And there is actually a paper by Van Veer and a collaborator who studied this problem using a tropical geometry, which I only partially understand their paper. And with tropical geometry, they can understand how things go to infinity, assuming x is shown. Again, he needs to assume x is shown. But if I want to drop the assumption x is shown, I don't know any result that can tell me, just maybe by looking locally, will there be points going to this part of the boundary, or where to the boundary points will go, how many will go. So far, without assumption of shown, I don't think people understand. Okay. I'm a bit ahead of time, but because there will be more talks, short talks, so I think I will just stop it. Thank you.
Questions? We have some time. Yes.
I actually have many. If you could go to the previous slide. So you say here that you compute local Euler construction by counting those critical points of various ML functions. So how do you count? I mean, do you use homotopy continuation methods? How do you count critical points of various ML functions? So, is it like a deterministic or a probabilistic algorithm?
Yeah, okay. That's a question you should ask Jose, but I mean, so my formula first tell you, if you count the numbers, you know the Euler abstraction. But how do you count more efficiently and count for larger dimension? I think, yeah, if you want to do higher dimension, I think if Jose is here, he will say use homotopy method. But you should ask him to get the more.
I mean, I have more, but if other people want to ask.
Are there other questions before maybe you can?
So in your formula where you described like the Chern-Mather class and Pn, could I take a different compactification for it? So for example, could I compactify by P1 Pn?
Oh, can I? Oh.
I want to compactify by P1 Pn. Can you tell me how to do this?
Okay. So you're okay. Very good question. So okay. So my interpretation is now you want to start with the affine variety, maybe x in Cn. Or x in theta. Okay. I see. Okay. I think so the theory theoretically will tell you it will be some intersection number. So the Chern class, there will be some intersection theoretic interpretation. And if I guess, I just take some special direction. I make UI to be special. And if you do get some numbers, most likely will be smaller than a general number. Those will be kind of different way you make it special. Will recover some of the Chern classes. Yeah, I think if you want to push the theory can be modified to answer a question, but I don't have an immediate formula.
Later, since we have 4 short talks, unless there are other. Okay, next.